Welcome to EDU World Space.
Okay, so this problem is about using a gyroscope to rotate a aircraft. And so I will say I struggled a little bit with this problem, but it's interesting. I love gyroscopes because they're still so non-intuitive, and I kind of hope to get an intuition on them. I'm working on it. But yeah, let's dive into the problem. So first, let's get down the givens. So IG is 20.0 kilogram meter squared. And IS is 5.00 times 10 to the 5 kilogram meter squared. And then the gyroscope has we can get it up to 100 radians per second. And so our goal is to figure out how long it takes for the spaceship to change its angle by 30 degrees. And so I think the idea is that you can initially say that the system has no angular momentum. And so then as you start this up, then the system is going to rotate, the spaceship is going to rotate in order to conserve that zero angular momentum. Okay, I paused the video to think, and I don't know what I said to make last to make this continuous. So I'm going to start and possibly repeat myself. So we can use angular momentum conservation. Basically, as we start this up, the gyroscope up, whatever angular momentum it has is going to be balanced by the angular momentum of the spaceship, right? So if it picks up angular momentum like IG omega G, spaceship has to have IS omega S. And you basically would want to orient the gyroscope such that the body of the spaceship rotates in the direction that you want. So if like the spaceship is like this, then what you want to do is kind of have your gyroscope rotating like into and out of the page. And then that way, if you want this to rotate this way, it's the angular momentum needed to do that is balanced by the angular momentum of the gyroscope. Because I guess in this case, the gyroscope would want to be like rotating counterclockwise. And the axis would be into and out of the page. And so these are the two angular momenta that would balance each other. And so we can say that IG times omega G is equal to the I of the spacecraft times omega of the spacecraft. So what we can do from this is get omega of the spacecraft. And that's IG omega G divided by IS. And so as this rotates, it's going to change its angle. So this is also equal to delta theta over delta time. And so we can equate these two to solve for time. So I'll just keep calling it delta time. I need to bring this over. It's kind of hard to visualize when they're not on the same line. So bring this over, flip this, and multiply by delta theta. Okay. So delta theta IS divided by IG omega G. Ooh, can I do this in my head? And then probably not, because 30 degrees is pi over 6 radians. And so we definitely need to use radians anytime you're calculating anything. Generally do not do degrees if you want to do the method of just putting everything in SI. I'm sure you know that by now if you're like all the way at the end doing gyroscopes. But just in case, I like to be clear about like every step that I do. So I'm plugging all this into a calculator now. Pi over 6 times I of the spaceship, which is 20. And then we want to take this whole thing and divide it by, I of the spaceship is 5 times 10 to the 5. 5 times 10 to the 5 divided by 20, and what else? Omega g, so that's times 100. And with that, I get 131 seconds.